So we'll continue from where we left off regarding Newton's third equation of state. We saw that both GR and nuclear forces are essential to understand neutron star structure. And the nuclear forces, as I said, the repulsive part of the nuclear force is not very well understood from or well measured from laboratory experiments. So there are uncertainties, and people try to estimate it by various kinds of extrapolations, and that's what gives you a degree of uncertainty in the equation of state, and correspondingly to mass radius relation and everything that follows. So let's just recall the basic features of the neutron star equation of state now. We already said this, the matter is actually degenerate. All species of particles, neutrons, protons, electrons, are primarily degenerate. It is hot, but the temperature is still much, much less than the Fermi temperature. So therefore, the thermal correction to equation of state is negligible. So we keep role of temperature as insignificant. I've also said that the matter is in beta equilibrium, which means that this is satisfied, and mu p mu n are just the Fermi energies here, or the effective Concur potentials, without the relativistic expression of mass. So that's why this is present here. Now, as you go to higher densities, you would find that when you look at the result of keeping this condition and also charge neutrality condition, that is Np is equal to Ne, and you add muons as well, then what will happen is initially the proton fraction starting from nearly 50% at the surface, it will keep going down. It will hit a minimum near the nuclear density, and then it will rise again, and as density tends to infinity, the proton fraction will saturate at 1/8. So deep in the interior, you can get about 10 to 12% of protons, and remaining being neutrons. And we will have electron number density equal to the proton number density for charge neutrality. So the nuclei get progressively neutron rich as density rises. Z by A starting from half goes to very small values, and beyond neutron drift point, nuclei will coexist with free neutrons. And when you reach nuclear density, then the nuclei will dissolve altogether. So there will be no nuclei left. You will only have free neutron C plus corresponding protons and neutrons. Now in core catalyzed matter for a given density, there is a fully understood fixed composition. The ratio of protons and neutrons and electrons are all defined. Also, temperature, as I said, doesn't play a major role. So in this case, the equation of state may be considered barotropic. So we have pressure as a function of density alone. We have already mentioned this, the degeneracy pressure alone is not enough, because if that were the case, then Oppenheimer-Volkoff limit is 0.7 solar mass, you will not get any of the neutron stars that we see. So nuclear interaction is key ingredient, but not well determined. So now let's take a little bit closer look at the construction of the equation of state. From our knowledge, whatever knowledge we have, either by direct measurement or by extrapolation or from a theoretical paradigm, we can predict something like a quantity like energy per baryon, which is a function of baryon number density. So put all the physics that you know, and then you can calculate this. Now once you have this quantity, then you can derive pressure and density from here. Let's say I plot baryon number, energy per baryon as a function of 1 by density. Let's plot it that way. Then you will have a curve like this. That is, as density goes up, energy per baryon also goes up. So blue curve is a representative representation of baryon number, energy per baryon as a function of number density. Now at any point where you want to evaluate the equation of state, take the corresponding number density, which is 1 by n, some value 1 by n, go to this curve and draw a tangent to that curve. If you draw a tangent to that curve, then you have a slope and an intercept. The slope of this curve is the pressure. And the intercept here, which is basically at n going to infinity, the intercept here is the chemical potential. Algebraically, this can be written as the pressure is n squared del EB del n, and the density, mass density that you are used to, is number density times energy per baryon. So that gives you the total baryon energy density divided by c squared. That's the mass density. So these two are the quantities that you need to then plug into your structure equation and solve it. And it's evaluating this quantity from known theories.
The mod value for the pressure it has taken, right? It is the mod value of the pressure it has taken, right? So there is always one minus sign is coming in front of it because of 1 by n. Because if you do del EB by del 1 by n, that is a pressure. So now del of 1 by n gives you 1.
Yeah.
So that
it is minus that. So this expression is what you are looking for.
So EB is negative because it's a binding energy it has been taken.
No, it's not binding energy. It is not a bound system anymore. Binding energy is coming from gravity. It's a repulsive system. EB is positive. So EB is positive here. So it is minus del EB del 1 by n, which is n squared del EB.
So definition of pressure is minus of del EB by del.
This is the definition of pressure, but it can be depicted easily if you plot it in EB versus 1 by n plane. Right? This is the definition of pressure. N squared del EB del n. Okay? So
I have one question.
Yeah.
So when we are looking into the EOS, so in the cold catalyzed matter there is a nucleons, right? There
Yes.
we have the heavy nucleons.
Yeah.
And since these nucleons are existing, that these nucleons are bound structure, right?
Nucleons are bound. Not nucleon, nuclei.
Nuclei are basically
Yes.
bound structures.
That is correct.
So then in that case, those bound structures will have some amount of binding energy, right?
Well, that will have. But then EB itself will be much larger than the binding energy, right? EB includes the rest mass and everything, right? So it's a total energy, total relativistic energy, which is, it may be slightly less than the total free rest mass of nucleons. But it's still a positive quantity. Right? Bonding energy will never make the sum equal to less than 0. You may have 938 MeV
Right.
minus 1 MeV.
Right.
It may become 937. So that's so it's still a very large positive quantity. So this is the total energy per baryon at a given density M. Okay. And it is in computing this quantity, and from nuclear physics you want to compute this quantity. And that's where the uncertainty lies, because we don't have proper measurements or very clear-cut theories. And why is that? Because we know that the theory of nuclear interactions is given by strong interaction. And nowadays we have a good understanding of what the strong interaction is. We have predicted various manifestations of strong interactions. They have all been verified. Standard model is doing reasonably well. So why is it that there is a problem of computing this energy per baryon as a function of density from first principles, which means from quantum chromodynamics? The problem is the following. I'll come to that in a moment. First, the problem is why it cannot be experimentally measured. So we have high energy accelerators in which we let ions which are raised to very high energies collide, and in the collision we can then probe what the result of the collision is, and that tells us about the forces at short distances. You want to go to higher energies because that then makes the de Broglie wavelength of the particle smaller and smaller, and the de Broglie wavelength is your resolution at the distance of the distance which you can measure. Now all that is possible in the lab, and accelerator energies are becoming higher and higher. The problem is we can do that, for example, in LHC and so on. But once you make this collide, the material becomes extremely hot. So you can measure interaction at short distances for very hot nuclear metal. That lies on the upper left hand corner, which could be relevant to what the early universe was like. But the neutron star equation state sits at the other corner, where you have high density. So the baryon chemical potential going up here means the density is going up. So as you go to higher densities, again, laboratory experiments will give you something in this corner. People are even trying to find and experiment with coagulant plasma in the accelerators. But it's impossible to produce this in terrestrial conditions, which is very high density but very low temperature. So laboratory experiments cannot access the neutron star equation of state from measurements straight off. And the problem with computing it straight from QCD is the following. If you may remember, the QCD is a theory where the coupling constant is large. Okay? In case of, if you draw a Feynman diagram, then at each vertex you have to put a coupling constant to evaluate the interaction. you can do this for electromagnetism, and the coupling constant you put at each vertex is your fine structure constant, which is a small quantity. And therefore, as you increase the number of orders of interaction, you get a converging series. So you get a result which can be evaluated. This is not true for QCD. In QCD, the interaction is very strong, and the coupling constant can become larger than 1. So you have to keep having to calculate very large number of terms, and it is not convergent. You can try to do this with the propagator, where you calculate the quark propagator and then compute the partition function. Your pressure, density, they are all derivatives of the partition function. You calculate the partition function by integrating the quark propagator times the action over all quark degrees of freedom. This is what lattice gauge theory is trying to do. But the problem is this quark propagator, when you go to large chemical potential, it is strongly oscillatory. So this is called the Fermion Sine problem. You keep one term, and the next term, the sign of the result will keep changing. So because it's strongly oscillatory, the direct integration does not yield any useful result. So you have a cancellation between two very, very large numbers to give you a very small number. So this problem has not yet been tackled properly. People are still making attempts.
Does that mean numerically it's a problem, or the theory
itself
is a problem? Okay.
And this is what lattice gauge theory is trying to do, but it has not yet been able to do.
But But in the future, the same thing can be used numerically and can possibly be solved.
No, lattice gauge theory is trying to do it numerically, right?
Right.
This is a problem in numerics.
Oh, okay.
Right? Because if you have two numbers of the order of 10 to the power of 33, and the difference gives you 10 to the power of minus 20,
Right.
then numerically it is very hard to keep track of.
Right.
So people are trying various regularizations, and then different regularization mechanisms give you different results. So this subject is still open. Objective is not yet realized. So because of this Fermion Sine problem, the route that people follow to find this EB as a function of n are one of two routes. So you do what is called a phenomenological extrapolation, which is model dependent. So either you do something like a mean field theory. You say, okay, I'm going to ignore all this exact calculation and so on. I will say that the interaction is approximated by a mean field, and then I will attribute some character to this mean field, and there will be some constants which define my mean field theory, and I will fit that to my low energy measurements. With the same parameters, I then extrapolate it to much higher densities. So these are called mean field theories, or RMF, relativistic mean field theories. So that gives you one family of equational states. That gives you an effective Lagrangian, and then you use the effective Lagrangian to create the action, and then you integrate it to get your equational state. Or you can start from the other end. You take the low energy laboratory measurements, where nucleon-nucleon interactions, particle-particle interactions have been measured with very good accuracy. Then you make a phenomenological potential model, which is basically some algebraic function with multiple parameters, which fits this many-body potential. you can measure that at a few densities, at few different values of n, and get dependence of these parameters on n at low densities. Now with this, then you extrapolate to high density. You have not measured in high density, but you say that, okay, so these parameters and the density dependence of these parameters is what I know at low density. I'll keep it, and then I'll extrapolate it to high density. So this is a more phenomenological, empirical way of.
So there is always some energy where these one is a IMF and where these two body nuclear potential or three body nuclear potentials, they merge, right?
Yeah. So they will fit in the results in that regime. All of them will try to fit the results in the regime wherever experiments are available. But these two are different ways of extrapolating to higher densities. So they have different sets of parameters, and the way they extrapolate to higher densities are different. Particularly all the nuclear potentials and so on, they are all non-relativistic.
They are all
So you take this non-relativistic regime and then just propagate it to high density without worrying about relativity. Mean field theories have relativity built into them, but have much smoother set of parameters, and then you just extrapolate to high densities.
Lower densities as well.
At lower density is where you start. You fix your parameters based on your fit to lower densities.
These are the parameters of
your theory. Of your theory or of your empirical model. Okay, so you fit whatever is known from laboratory. And then you have to go to much higher densities, so much higher values of n, where there is no measurement. So that's what people are doing. These are different ways of extrapolating from laboratory measurements. However, if you go to very high densities, then this kind of approach becomes reasonable. You can actually get a result which is convergent, which is closed. Because once you go to very high densities, the quark-quark interaction approaches asymptotic freedom. So the coupling constant goes down. As the coupling constant goes down, all the series become convergent. So one wishes that neutron star interiors were in that regime, but it is not. For that, you have to have densities in excess of 10 to the power of 18 grams per cubic centimeter, where neutron star interiors do not reach. So we are caught in this sort of barren region of theory and measurement, where you cannot compute it correctly accurately from theory either, and neither does any experiment exist.
But how do we know that it cannot reach?
Yeah, if you put 10 to the 18 grams per cubic centimeter, then you will find that you are well beyond the maximum mass. So you will not be able to. You will not be able to support a neutron star with that kind of matter.
But this is assuming it's purely quark matter, right?
No. Actually, you take any equation of state, you extrapolate it to 10 to the 18, and then try to create a neutron star. So no equation of state will reach 10 to the 18 grams per cc at the center. It will not give you a stable star. Is that clear? So this is the problem. So that is why we have all these uncertainties. So just to highlight the difference between terrestrial matter and neutron star matter, in terrestrial matter what we can do is to look at low densities, densities less than nuclear density, and terrestrial matter is nearly symmetric. All this matter we see around us, Z by A is roughly equal to half. Whereas in neutron star matter, we are talking about high densities, supranuclear densities, and matter becomes very asymmetric. So, at the core of the neutron star, you may have at best 10 to 12% protons, mostly neutrons. So any interaction that depends on high power of density or high power of asymmetry is going to become very sensitive to small inaccuracies in your extrapolation when you go to neutron star matter. So to make it difficult to predict the behavior of neutron star matter based on laboratory data, if your model has strong dependence on either density or asymmetry. And this is unfortunately the problem. Okay, so what else we have to worry about when you go to high densities? When you go to densities below nuclear density for cold catalyzed matter, I think from all the information we have, we can predict the equation of state very well. There is not very much of a dispute about what the equation of state looks like below nuclear density. Once you go above nuclear density, many body interactions start playing a critical role. And as your Fermion energy begins to rise, it becomes possible to create other particles. For example, other mesons, other hyperons, they all begin to appear depending on what the net energy density of matter becomes. So that's here you assume certain equation of state, and you can see that as you go up in density, at different points, these different particles will begin to appear. Because their rest mass now is less than the energy per particle that you have reached at that density. These include hyperons, heavy mesons, quark matter, condensates. All of these will be included. Now, many body calculations also people have been doing for quite a while now, going up in order. NLO is next leading order, NNLO is next leading order, and so on. So now let's take the prediction of many body calculations from nuclear matter. This is energy per baryon in MeV, and this is density, number density. This is only going up to nuclear density here. These are different sets of calculations. And you can see that as you approach nuclear density, the predictions begin to differ from each other quite a lot. So therefore, the uncertainty begins to increase. And this is one of the major contributors to uncertainty in neutron star equation of state. So many body interactions play a critical role, and it remains a major source of uncertainty. The next thing to look at is the symmetry energy. I mentioned that the laboratory matter is symmetric, where proton fraction is half. If it is pure neutron matter, then X is 0. In case of neutron star matter, X is small, maybe 0.1 or thereabouts. The energy per baryon at a given number density is not does depend on the number density alone, but it also depends on the proton fraction. If you have material at the same number density but different proton fraction, you will have different energy per variance. So this is represented by your symmetric component of energy per baryon plus a power series expansion on x. Actually, it's written as 1 minus 2x squared, so if x equal to half, then these terms go to 0. And this is called the symmetry energy. The next term is called the symmetry energy. The symmetry energy itself is density dependent. For a given value of x, you have the symmetry energy is density dependent. It can then be expanded in density as departure from nuclear saturation density. So this is nuclear density, Ns. And you have these coefficients, Sv, which is the constant, L and Ksin. Usually these three constants are used to represent symmetry energy.
What is Ns here?
Ns is nuclear saturation density or nuclear density as we call it. If beta equilibrium is imposed, then pressure at n equal to ns is determined solely by the first term here, Sv. And solely by Sv and L in this quadratic approximation. And this pressure is actually strongly correlated with the neutron star radius. So if you take pressure at nuclear density, the radius of the neutron star seems to be very strongly correlated with the value of pressure at nuclear density, at nuclear saturation density. It depends on that much more than any other aspect of the equation state.
So Ns and radius, yes.
Pressure at
Pressure at Ns
is strongly correlated with the radius.
and
So if you are able, from your theory, if you are able to predict the pressure at Ns very well, you can get a very good approximation to radius, but not mass. Neutron star mass radius relation, I will show a diagram shortly. If you recall it, it sort of rises very steeply as a function of mass, mass on the vertical axis, radius on the horizontal axis. So different equations of state have these
shifted.
horizontally shifted more or less. And that value where it keeps going up steeply, that is more or less the characteristic radius in that equation of state. And that is closely related to the pressure at nuclear density. And as I also mentioned, that species at high density include hyperons, mesons, quarks. Now with quarks, something interesting may happen. If you go to high enough density, you can get a phase transition to deconfined quarks perhaps. And you would have strange quark matter also appear because the energy per baryon has now gone above the strange quark mass. And this combination of UDS matter, ground state, people have shown that this could probably be a ground state which is below the ground state of nuclear matter that we know. So this represents a ground state which is lower than the nucleon ground state. Which means if you now bring this matter in contact with any regular nuclear matter, irregular nuclear matter will transmute into this matter. Only thing is, to produce this matter, you have to first go through a very high density. So you have to first compress it high enough so that you go above the limiting density so that your quark matter ground state can be produced. If you produce such a core inside a neutron star, then this matter will eat away at the rest of the star and everything will get converted to this quark matter state. And such stars are called quark stars. Okay. Now these quarks have a form of interaction which is sort of asymptotic freedom. When they are very close to each other, they don't feel the interaction very much. They are like free particles. But you try to separate them, strong interaction will try to keep them in. So these quark stars can represent fully self-bound configurations. They don't require gravity to keep them together. Their own interaction will keep them together. You cannot avoid gravity. Because of the presence of gravity, what will happen is this will have a maximum mass. Gravity was not required to keep them together, but gravity will still dictate how much mass you can hold up by this point. Now all of these effects, whether it's hyperons, mesons, quarks, any of these particles, if they appear, they will soften the equation of state with respect to the regular nuclear equation of state. You have a question.
So when this quark ground state get formed, if they get formed, so it has to go through one energy barrier, right? And then
Density barrier. Basically.
Yeah, basically density barrier,
Yeah.
energy density barrier, basically. Right? Now, once they get formed, if, as you said, means they start they start transmuting everything, but as it's going out, it again has to face that energy barrier, right? Now,
No. So now all matter will become more dense. It will convert the matter and the density will increase all throughout. So once you have formed this matter and other matter comes in contact with it.
if they don't come, they won't.
No, if you have a physical separation, then no. So the people have speculated how can a quark matter have a quark star have a crust. So ideally, if everything is in contact, it will have no crust. It will have only this matter and nothing else. So the speculation is that if you have a quark matter star, because there are these are charged particles, and in the final equilibrium configuration, you can have a net residual charge on the quark star. And this net residual charge can then sit on the surface of the star. And then you can have a skin of matter which is sitting on it, which is electrostatically held apart from the quark matter surface. So you can have an electrostatically suspended crust of a certain amount of mass, it's a small amount of mass. So people who have tried to model, for example, pulsars using quark stars would have faced this problem as to how do you have a crust. You need a crust, a solid crust to have something resembling pulsar. So this is the answer to that. So you can have a non-contact electrically suspended crust, which can have a very tiny amount of matter, but may be sufficient to give the essential features of a solid crust. But if it does come into contact, then you will have conversion.
So then in this case, again, like in what happened previously, as it goes across the energy, this density barrier, now as it starts producing a quark core, Now it will also have some, it can also end up having some residual charge, right? And then as it's propagates, so now they are kind of, say, in a process of transmutation of these quarks to their nucleons to quarks. So there is a kind of layer, and then there's, for the charge neutrality, it can again start producing this kind of layer in between, right? Which can keep on.
No. So, you cannot have infinite amount of mass held by electrostatic repulsion. So only some little bit of matter on the outside can be held. Otherwise, due to gravity, it will fall. It will overcome the electrostatic repulsion, it will fall on the star. So again, as soon as it falls on the star, you will get conversion. So it will stop when a skin of only that amount of matter is left. Until then, everything will keep accumulating in the inner part of the star. Okay? So now, what kind of experimental observational constraints are we able to derive on the equation of state, which can then tell us something about the property of nuclear matter? So we do have laboratory constraints. For example, we can measure nuclear binding energies. Nowadays, you can measure neutron skin thickness. So if you take a heavy nucleus, where there are lots of neutrons and lots of protons, then you can measure the extent of the wave function both in neutron matter and proton matter. Then you find that the neutron matter wave function is slightly more extended than the proton matter wave function, and that's called the neutron skin thickness. And this is a critical component in determining nucleon-nucleon interaction. Polarizabilities of these nuclei is also giant dipole resonances. These are all that can be measured in laboratory experiments, and all of these go in to make the model of nuclear interactions. Then we have astrophysical constraints. We have measurements of neutron star masses, measurements of radii in some cases. We know the spins. We can measure oscillations in some of them. And more recently, we have access to the measurement of tidal deformabilities. All of these can also put constraints on neutron star behavior. In addition, there are general constraints, for example, causality. Many of the equations of state which you build based on the nuclear many-body theory, because you start with a non-relativistic framework, when you go to high densities, the sound speed in the medium may exceed the speed of light. So you cut out those portions of equation. So sound speed should not exceed speed of light, so causality condition has to, you can impose. One can impose also thermodynamic stability condition, which means that the energy density should be positive definite and monotonically increasing function of pressure. So now you have all these zillions of models, only a few are plotted here. These are equations of state. This is pressure versus density. And this blue region shows you allowed equations of state which satisfies all these constraints. So all those which fall within this blue region are allowed. So take this region of allowed equations of state and use TOV equation. Then you can populate the mass radius diagram of neutron stars with different lines, one corresponding to each equation of state. And this is why I was mentioning that if you go from one equation of state to another, typically the line will move from one place to left or right. And the curvature at the upper end, that can go up and down. So this decides the maximum mass, and this decides the typical radius. There is a causality limit, which means sound speed should not exceed the speed of light. Then, okay, so let's.
How this causality limit is basically means how that line is basically constructed in the MR diagram.
Now you take equation of state where sound speed is equal to c. Then you will get a.
Oh, I
mass
can
radius.
do dp d rho.
Yeah.
At all the points where it goes to c, I just
That's
put that line.
That's what the causality line is.
But in MR diagram, how I am putting that value?
Or any equation of state where dp d rho equal to c, you can find
What is the mass and
radius, right? So now this is a compendium of measured masses of neutron stars. Some of them are measured to have fairly high masses but with large errors. So for putting constraints on equation of state, people are careful. They take measurements with the smallest possible errors. And the highest value of mass with the smallest possible error is this one, so far. It's 2.01 plus or minus 0.0. This one has a large error, but people could be considering this if the error goes down. There are some systematics which may still need to be reduced for this to be considered reliable. But if it converges to this value which is measured here, then it will produce a much stronger constraint. Right now, the strongest constraint for mass alone comes from this object. So the minimum value of the maximum mass of the neutron star has to be above 2 solar mass. If your equation of state did not produce at least 2 solar mass neutron star, then that will be ruled out. Now, many such equations of state did exist. They have all been excluded from this diagram because of this constraint. Here again, there is a compendium of equations of state with some of the measured masses represented here. J0348, which I just mentioned, is over here, with these dotted lines giving you the error bar. Villa X1 is a heavier measured mass, but with much larger error. And here are how different equations of state prediction for mass radius relation looks like. And you can see that certain families of equations of state actually survive, and there are others which some of them are not plotted here. If these went below this, they are ruled out. There are two families of equations of state. The rightmost ones, the stiffest equations of state giving you largest area, they are mostly all from relativistic mean field theory. And extrapolation from measurements of nuclear potentials, they all lie in this much. Now that's from mass alone. To get a better idea of what equation of state looks like, you should also try to get a constraint on the radius. For that, people have been trying for a long time. X-ray bursts is one possibility, where you take thermonuclear explosion happening on an accreting neutron star surface, and then as the explosion occurs, the radius expands. And as the radius expands, you see a rise in luminosity. The radius expands because of luminosity. And once it reaches Eddington luminosity, then it lifts the surface. So therefore the maximum luminosity you reach can be identified as the Eddington luminosity at the surface. And Eddington luminosity gives you a measure of the mass of the star. And then surface will expand and then fall back. Material will become transparent, so you will begin to see the surface again. So there you will have measure of both luminosity and temperature. From that you can measure the radius. So that's what is done. We look at luminosity, the maximum point here attribute to Eddington luminosity, and temperature, black body radius. If you see, the black body radius increases and then drops and then keeps steady. So this steady portion starting from the drop is attributed to the neutron star radius. The black body temperature also then goes to maximum here and then it cools. So now there are these things are coupled because of GR, the temperature, luminosity as the observer sees depends on the surface redshift. So you have to include all that in, and then you get two coupled equations which if you can solve, we should be able to get mass and radius. So people have been trying to do this for a long time, but there are many uncertainties. Yes.
Things are not clear actually how this is, how it's getting the estimate. Actually, you're saying that expanding this, I didn't get how expanding this expansion of surface is increasing and it's again falling backwards.
Expansion happens because luminosity reaches Eddington luminosity, right? It is expanding due to radiation pressure.
Yes. So,
right? So it is accreting matter which now gets lifted because of radiation pressure.
so it's an accreting neutron star,
Yes.
and then some,
Matter is falling on the surface,
right?
and then at some point on the surface nuclear reaction is ignited.
Okay.
So there is a lot of sudden production of radiation. It then lifts up the accreted layer.
Oh, okay.
And that lifting happens because of radiation pressure.
Right.
So therefore the luminosity there has to be the Eddington luminosity.
Yes.
Okay.
Hmm.
So that's the maximum luminosity. You attribute it to the Eddington luminosity. And then the reaction is over, it will cool. And the material that is expanding, it may continue to expand, but as it expands, it will become optically thin. So you can see through it, and you can the effective black body radius will collapse back to the surface once this becomes optically thin. So you're actually seeing the surface there.
So when extra outburst is happening at that time, I'm getting some flux, right?
Yeah, this is
That is
profile of an
FX.
extra outburst.
That is FX, right?
Yeah, this is Fx. Well, it's converted to Lx from distance, but it's Fx.
Okay. And then how I'm getting back?
So you're measuring not just flux, you're also measuring the spectrum, measuring the temperature,
Yes.
right? So measuring these two quantities, Lx and temperature, as a function of time, right? So therefore, at any point of time, given luminosity and blackbody temperature, you can tell what the radius is.
From this relation.
Yes, which is this. So you see the radius first expands because the surface, the material gets lifted, and then it becomes optically thin, and then you start seeing the surface, neutron star surface itself. So this steady value of size of the surface is what is attributed to the neutron star surface, neutron star radius. So that's what it is. Only problem is in X-rays we are always looking at only a small energy band. There could be a lot of energy outside this band. The shape of the spectrum, it may have components other than blackbody components. So there is always a problem there. People use something called FC here, it's called color factor. which is a guess value of how much energy you are missing.
From other wavelengths.
Yes.
So
Polar
typically,
corrections.
what are the typical uncertainties that people get from this kind of observations on radio?
Yeah, I'm coming to that. So now if you put all of that together, you can take some of the best cases for which this measurement can be done. So it's from same data recovered using two different values of redshift. One is redshift set at the surface redshift, set in Z page equal to ZR, and is redshift set to 0. Just for comparison. And you can see that you have different islands of confidence, where you are getting measurements which are here it gives you some 8 kilometers and 9 kilometers. Here it gives you something like 10 kilometers with masses around 1.5 to 2 centimeters. But clearly, these measurements are not constraining enough to really pin down your equational state. It's not reached that level yet. Then there are measurements from quasi luminous extremities, where luminosity is due to cooling from deep crustal layers. I mentioned to you that the cold catalyzed matter is fine for a neutron star which is formed initially and just had time to cool for a million years. But if you're accreting matter, you're continuously adding new material on the surface, and it may not have had time enough to go to cold catalyzed matter yet. So deep in the crust, there is still transmutations happening, and this continues to heat the crust. And this deep crustal heating keeps the surface hot, and over time, cooling occurs. So this luminosity from quiescent elements will occur because quiescent meaning it's not accreting right now, but it's still hot surface, and due to cooling from deep crustal layers. Now you can model the spectrum that you get from the surface, common emission, with radiative transfer through the atmosphere, where there are magnetic fields, other materials, and so on. And the spectral modeling can then yield radius, effective temperature, and surface gravity if you model it well. So uncertainties arise A, from the distance to the object, B, the atmospheric composition. This is not cold catalyzed matter anymore. It's coming from accreted matter, so you don't know whether there's a lot of hydrogen in the atmosphere or some helium in the atmosphere and so on. As well as interstellar absorption, that needs to be very well known, because here you are looking at very soft X-rays. So the best constraints that you can get here, I mean, there is a better constraint from a more recent paper which is not yet published, but it's somewhere around 8 to 10 kilometers. It's been moved a little up in the more recent work. You can get constraints of spin as well. If the radius is large, the spin will be restricted to a smaller value from centrifugal limit. This is a simple consideration. Now you have to do a more sophisticated calculation of it using GR, using all the complications that occur because of rotation having to be included into metric as well. But no matter what you do, it looks like a typical neutron star should have fastest rotation periods, which are sub-millisecond. However, in all the neutron stars we know, the fastest rotation rate we know today is 716 Hertz. Why is that so? So the question is whether in the process in which neutron star acquires spin, there are processes which limit that effect. For example, if it is being spun up by accretion, then is there also an angular momentum loss from the neutron star spin because, let's say, gravitational radiation? In that case, if you postulate such a balance, then that can lead to some constraint of the equations. Okay. Now, next was pulse profiles. This is a technique which is being tried in great earnest today. This is X-ray pulse profiles. An X-ray emission from isolated pulsars. The pulse profiles there are not sharp pulse profiles like in radio. They are more like this. There are two reasons for it. One is the radio pulse profiles are created by highly relativistic forward moving particles, so therefore you get a beaming. That is not true in X-rays. You are looking at hot surface. So each point of the surface gives you a near isotropic emission. Secondly, emission coming from the surface undergoes a fair amount of light bending because of general relativity. So it then smoothens out the outgoing direction even more. So once you put all the effects in, then you can, for a point hotspot, you can ask what kind of profiles you will see. So for example, flux and temperature, color. You see profiles like this. So this is your sinusoid, the dashed one, but you see the flux will look slightly different because of Doppler shift. When there is a spin, there is a Doppler shift, and that causes asymmetry. And that is much more pronounced in color. So you have to take into account light bending, Doppler effect, propagation delays, all of that, and then look at the pulse profile. And you can see that the color and the flux has some phase difference. And this phase difference depends on radius and mass. So you measure the phase difference, and if you know the spin, then from these curves, depending on your measured phase difference, you can then try to get a constraint in radius and mass. And this is what NICER is trying to do. The NICER mission is built to do just this. This is the prime objective. NICER is the name of the mission, you know, it is Neutron Star Internal Composition Explorer, right? And this is how they expect to explore the internal composition. Okay, so I think what I'll do is I'll stop it here, and Wednesday I'll finish the rest of it and also do a little bit of interior condensed matter physics, like superfluid superconductivity, and finish it.